Welcome students on today's lecture on circular water tank with the fixed base. Okay, in the previous lecture we have come across the design tables according to IS 3370 part for calculating the bending moment, hook tension and shear at the base. So we'll just go through what all we have done in the previous class. So this was the given data, and this was the dimension decided, wherein diameter was 11.5 meter and height was 4.2 meter, and the thickness of the wall and base slab was taken as 200 mm. Now, bending moment, fourth point, that is this bending moment, ring shear, and ring tension was computed according to the IS code of practice for concrete structures for the storage of design liquids, part for design tables. Now in this we had five conditions according to the clause 3.1. We'll just go through it. So our condition was a cylindrical water tank, so circular water tank. So calculation of ring tension and movements in the wall according to the code book. So walls with a fixed base, free top and subjected to triangular load. So this was the condition for our given numerical. Apart from this, there are many other conditions. So we need to check in the question paper what is the condition. So let us see what was given here. So here it was given as walls built continuous with their footing are sometimes designed as though the base was fixed and top free. Although strictly speaking, the base is seldom fixed, but it is helpful to start with this assumption and then go to the design procedures for other more correct conditions. Ring tension at so this is about calculation of ring tension. Ring tension at various height of the walls of cylindrical tanks, fixed at base, free at top, triangular load is given in table number 9. So according to table number 9, we compute the ring tension. Then the bending moment. So here you can see the bending moment in cylindrical wall with fixed base, free top and separate triangular load is calculated according to table number 10. And coefficient of shear at the base of a cylindrical wall are given in table number 11. So this is how it looks. So let us go to these three tables. So table number 9. So this is table number 1. So this is table number 5. So let us go to table number 9. Okay, so this is page number 35 of the IS code, and this is how we calculate the ring tension. So table number 9 gives the description at in tension in circular ring wall, fixed base, free top and subjected to triangular load. Now this is how ring tension formula is given. Ring tension T is equal to coefficient into omega H into R, where R is the radius, H is the height and omega or W is the density. So for this what we require this component h square divided by dt. So if you see here, we have calculated h square divided by dt considering the full height of the wall. So 4.2 square divided by 11.5 into 0.2, it is working out to be 8. It is working out to be 8. So we refer to this table. So working out to be 8 here, you can see this is 8. Okay, and we checked it for 0.6h, 0.6 of height, which is plus 0.575. So the coefficient is plus 0.575. So this value is substituted here in the coefficient, and omega WH into R is computed. So you can see the calculation here. So I'll just show it to you. So you can see plus 0.575 and the coefficient is this. So computing this ring tension, we got it as plus 0.575 into 9.84 into 4.2 into 6.25. So T tension is working out to be 148.069. Now let us see the other parameter. So table number 10. Table number 10 gives the bending moment here. So movement in cylindrical wall, fixed base, free at top and subjected to triangular load. So how do we get the movement? Movement is nothing but coefficient into WHQ, kg meter per meter. So let us see what is there. So h square divided by dt is already calculated, so it is 8, and we will consider 1h full h, so it is minus 0.0146. So substituting, you can see a minus 0.0146 into 9.81 into 4.2 cube, which is working out to be 10.61 kilonewton meter per meter. So let us see the shear at the base in the table number 11. So this is table number 11. So shear at the base of cylindrical wall. Now how is the shear given? V is equal to coefficient into WH square kg, because ours is the triangular load. So let us see. So our value for h square by dt is 8, and the triangular load for fixed base is plus 0.174. You can see. So this plus 0.174 will go here, and W into H square is computed. So you can see here plus 0.174 into 9.81 into 4.2 square, which is working out to be 30.11 kilonewton at the base. Now let us see the further computation. So next we have to design the section. So for M20 concrete, sigma CBC 7 and Fe415 steel, sigma ST 150 MPa. So from table number 21 in IS 456 2007. So 2000. So you need to go to IS 456 table number 11, wherein you can calculate this. So sigma CBC is given by is equal to 3 sigma CBC divided by FCK, 2 by 3 into 20, so which is working out to be 7 Newton per mm square. So K is computed next. So K is equal to M into sigma CBC divided by M into sigma CBC plus sigma ST. So 13, M is 13. So modular ratio, so 13 into 7 divided by 13 into 7 plus 150, which is working out to be 0.877. So J is equal to 1 minus K by 3, which is 0.874, and Q half of sigma CBC J into K, half of 7 into 0.874, 0.377. Q is equal to 1.153. So remember, the design of circular water tank is according to the working stress method. So this whatever we are computing K, J and Q is according to the working stress method. So D depth, minimum depth is equal to F divided by QB. So movement we have calculated, that is, you can see 10.61 kilonewton meter. So 10.61 into 10 raised to 6 divided by Q value is 1.153, and width will take as 1000. So it is working out to be 95.97 mm. So let the 200 be the thickness of the with effective cover of 40 mm. So T is equal to 160 mm. So steel for the bending moment. So AST, area of steel, is calculated M upon sigma ST J into D. So 10.61 into 10 raised to 6 divided by 150 into 0.874 into 160, which is giving out 505.81 mm square. So let us calculate the spacing. So the spacing is given by considering the 16 mm diameter bars. So spacing equal to for 16 mm diameter bars, pi by 4 into 16 square into 1000 divided by 505.81. So and maximum is 3 into D, where 3 into 160 mm 480 mm. So this component is working out to be 397.38 mm center to center, and here it is 480 mm. So providing 16 mm diameter bars at 300 mm center to center as vertical reinforcement on water face. Now let us compute the steel for hoop tension. So AST is equal to T upon sigma ST. So 148.069 into 10 raised to 3 divided by 100. Why sigma is T? Because steel will take the tension. Hence, the tension value is computed with sigma ST. So 1480.69 mm square it is working. So taking 12 mm diameter pass, we'll calculate the spacing. So the spacing of 12 mm diameter pass. So this is uh, here we have calculated sigma st. So 1130 into 1000 divided by 1480.69. So this comes according 113 comes according to pi by 4 into d square, where d is 12 mm diameter. So this is working out to be 76.38 mm center to center. So providing 12 mm diameter bars at 75 mm center to center adds hoop reinforcement on water face. So provided steel 113 into 1000 divided by 100, which is 1130. So check for tensile stress. So sigma C is equal to T divided by 1000 T plus M minus 1 into AST. So the hoop tension we have calculated, which is 148.069 to 10 raised to 3. Then we have 1000 into T is 200, that is thickness, plus M is 13 minus 1 into AST 1130, which is working out to be 0.69. So permissible we calculate by 0.27 root of SCK. So 0.27 root of 20, which is working out to be 1.2 Newton per mm square, which is greater than sigma C, hence safe. So this 1.2 is greater than 0.69, hence it is safe. So let us see about the distribution steel now. So minimum area of steel is 0.24% of the concrete area. So let us see the concrete area. So area of steel is equal to 0.4 divided by 100 into P into D. So 1000 into 200 mm, which is equal to be 480 mm square. So 8 mm diameter bars, let us calculate the spacing. So pi by 4 into 8 square into 1000 divided by 480, which is 104.7 mm center to center. So providing 8 mm diameter bars at 100 mm center to center as vertical and horizontal redistribution on the outer face. Now the last step is design of base slab. So base slab, we have taken the thickness 200 mm. So slab rests on the firm ground. Hence minimum reinforcement. So 0.24 divided by 1000 into 200, which is 480 mm square. On each face, hence it gets divided by 2. So 240 mm square. So the base slab diameter was considering 8 mm diameter was. So pi by 4 into 8 square into 1000 divided by 250, which is working out to be 209.43. So providing 8 mm diameter bars at 200 mm center center as vertical and horizontal distribution on the outer face. Now the last step, 7th step, is check for shear stress. So maximum shear at base Q is equal to 30.11. So you can see the page number 6, 3.2.2. Okay, I will just take you there. Okay, now according to the clause on page number 6, you can see the total shear stress is given by 2V is equal to Q divided by P J into D, where Q we have already calculated 30.11 into 10 raised to 3 divided by B 1000 into J 0.874 and into 160, which is working out to be 0.215, which should be less than 1.7 Newton per mm square. Hence safe. So we will see the reinforcement in the previous class. Meanwhile, we'll see what is given on page number 6 here. So the shear coefficient, the values of shear force along the edge of a tank wall would be required for investigation of diagonal tension and bond stresses. Along vertical edges, the shear in one wall will cause axial tension in the adjacent wall and should be combined with bending moment for the purpose of determining the tensile reinforcement. Shear coefficient for the wall panel of width B, height A, and subjected to hydrostatic pressure due to liquid density W, considered fixed at two vertical edges and hinged at top and bottom edges are given in table number 1, figure number 1 and table number 7. Shear coefficient for the same wall panel considered with fixed at two vertical edges and assumed hinged at bottom but free at the top edge are given in figure number 2, table number 8 and 2.33. It would be evident that table number 7 that the difference between the shear for B by A equal to 2 and infinity so small there is no necessity for the computing coefficient for intermediate values. When B by A is large, a vertical strip of slab near the midpoint of the B dimension will have essentially as a simply supported one way slab. Total pressure on a strip of unit height is 0.5 W A square, of which two-thirds or 0.33 W A square is a reaction at the bottom support and one-third or 0.17 omega A square is the reaction at the top. It may be seen from table number 17 that the shear point at midpoint of the bottom edge is 0.329 W A square for B by A2. The coefficient being very close to that of 1 by 3 for infinity. In other words, the B by A greater than 2, then that is correct only when the top edge is supported and not infinity. So this is how it is given. So let us go to the table number 7 and see. So you can see shear at the edges of wall panel is in top. So this is given according to these clauses you can see here. So this is in table number 9 also and table number 17 here. So this is how we calculate coefficient into the moment. So this is the clause explanation and this is the reinforcement which you have calculated and provided distribution steel in the walls for the outer face, for the water face, also of the base slab for both the faces. So this is the end of the design. So we'll see the detailing of reinforcement in the next class. Thank you.